And welcome back as we continue our cosmic journey. Let's go ahead now and use the HI diagram that we have previously explored and connect that back to our study of stellar evolution. So when we use this, we need to first examine this from the lens of the stellar life cycle. One of the best ways to summarize how a star or a protostar even changes with time is actually to use the HR diagram. If you recall, when we're looking at the HR diagram, the temperature is plotted increasingly toward the left. And as a star goes through the stage of its life, we'll find that its luminosity and temperature change. Thus, the position that we have on the HR diagram, in which luminosity is plotted against temperature, is also going to change. So we conclude that as a star ages, we have to replot it in different places on the diagram. Therefore, astronomers often speak of a star moving on the HR diagram or of its evolution tracing out a path on the diagram. So to estimate just how much the luminosity and temperature of a star change as it ages, we actually have to use calculations. Now, those are going to be calculations beyond what we're going to cover here, but that's how we, of course, derive this. Now, theorists compute a series of models for a star, with each successive model representing a later point in time. Now, stars may change for a variety of reasons. Protostars, for example, change in size because they are contracting, and their temperature and luminosity change as they do so. Once nuclear fusion begins within the star's core, main sequence stars change because they are using up their nuclear fuel. For example, they might move from the proton-proton chain to more of the carbon-nitrogen-oxygen chain. And so we can introduce this idea of evolutionary tracks. And the way we do this is through a series of points on the HR diagram that allows us to actually follow the life and the changes of the star. Now, if we look here at this diagram here, we of course have our familiar surface temperature, which is plotted in reverse. We have our luminosity, which is plotted up here. And the number next to each track, or onto the dark points of that track, is the rough number of years it would take an embryo star to reach that stage. You'll note again that the surface temperature increases toward the left. So again, we have that denotation so we can make sure that we are not mixing it up with how we are used to reading graphs. And the more mass that we add to a star, the shorter time it takes to go through each stage. So for example here, if I take a look here, here's an example of my different solar masses. I have a 30 solar mass star. You can see, of course, the different plots here with that star. We have a 10 solar mass star, a 3 solar mass star, a 1 solar mass star, half a solar mass, and 0.1 of a solar mass. If I follow, for example, the 1 solar mass star, which is, of course, our own sun, you can see how it would move through its cycle here, as we would, of course, move it as it slowly transitions through the main sequence. So here we have a zero-age main sequence. That is, of course, this line right here. And we can see, again, how it's going to move through that cycle. If I looked at something more like a 3 solar mass star, you can see how that line is also going to change as we were to plot the evolutionary track. Now, if we look at this in terms back of our protostars that we talked about, keep in mind that a protostar remains relatively cool with a very large radius and very low density. And during the protostar stage, it is very transparent to infrared radiation, and the heat generated by gravitational contraction can actually be radiated away freely into space. Now, because heat does build up slowly inside of a protostar, the gas pressure remains pretty low, and the outer layers fall almost unhindered toward the center. Thus, a protostar is going to undergo a very rapid collapse in the stage that corresponds to these rough vertical lines. So again, if we go back and look at that graph right here, you can see in here these, again, rough vertical lines that we are using to represent that here in our luminosity. Now, as the star shrinks, its surface area does get smaller, so its total luminosity is going to decrease. And we, of course, saw that as we looked at there, how the lines of those stars change. The rapid contraction only is going to stop when the protostar becomes dense and opaque enough to trap the heat released by gravitational contraction. Now, when the star begins to retain its heat, the contraction, of course, is going to become much slower. And changes inside the contracted star are going to help keep the luminosity of stars, much like our own sun, roughly constant. We can see how, looking at that diagram, how the lines all kind of more flattened out. That's that constant that we're looking at. So the surface temperatures, of course, are starting to build up, and the star is going to move to the left in the HR diagram, as we saw with those arrows as we trace their various paths. Now, the stars do become visible only after the stellar wind described earlier clears away the surrounding dust and gas. This can happen during the rapid contraction phase for low-mass stars, but for high-mass stars, they tend to remain shrouded in dust until they end their early phase of gravitational contraction. Now, when a star's central temperature becomes high enough, we'll say about 12 million Kelvin, to actually fuse hydrogen into helium, we can actually say the star has reached the main sequence. It is now a fully fledged star. It's sitting in equilibrium between the gravity and the pressure, and its rate of change has now slowed dramatically. Now, only the gradual depletion of hydrogen is what we really have to worry about as it's transformed into helium in the core, because that's ultimately what's going to change the star's properties. Now, the mass of a star determines exactly where it falls on the main sequence. As we saw, we had a couple different options there. For example, we had a 1 solar mass, a 3 solar mass, a 10 solar mass. Massive stars on the main sequence, we're going to see, have very high temperatures and very high luminosities. Again, that's what we saw on that track. Whereas we had the lower mass stars, we saw that their temperature was much lower, and they therefore had a much lower luminosity. Now, the lower end of the main sequence stops where stars have enough mass to sustain nuclear reactions at a rate that can stop gravitational contraction. Now, this critical mass is calculated to be about 0.075 times the mass of our own Sun. Now, objects below this critical mass are typically either going to be brown dwarfs, or if they are even smaller, they will end up as simply planets. At the other extreme, the upper end of the main sequence terminates where the energy radiated by the newly formed massive star actually halts the accretion of additional matter. Now, if we look at the upper limit of what we can find for stellar mass, we find that this tends to be between 100 and 200 solar masses. And so we can use this to kind of wrap these ideas back into an evolutionary timescale for our stars. How long it takes a star to form really depends on how much mass the star has. The numbers that label the points in each track, of course, are the times and years required for the embryo stars to reach the stages that we've been discussing. Now, the stars' masses that are much higher than our Sun reach the main sequence in anywhere from a few thousand to a million years. However, if we look at something like our own Sun, it took millions of years before it was born because it had a much smaller mass. And actually, if we wanted to go even smaller, we need tens of million years for those stars of lower masses to evolve into the lower part of the main sequence.